Now, today in this lesson, we are going to see two types of proving, one of them by counterexample, another by contradiction. So let's start with the by counterexample. What does it mean? For example, you will have a statement. Let me go with the daily life. If I say all apples are red. Okay, so it's my statement. And in mathematics, of course, we're going to have mathematical statements. So I'm just trying to explain the idea. If I say all apples are red, if you believe that this statement is incorrect, you just can bring one counterexample to disprove this statement. So it's also one way of proving, so disproving. So no such statement exists. So what you can say here, you show one. If you bring me one green apple. Okay, it looked like P. Okay, one green apple. So it kind of disproves my statement. So this one is disproving by counterexample. Let's see in mathematics how we can do it. For example, show by counterexample the following statements are not true. So it says first then, if n is integer and n squared divisible by 4, then n is divisible by 4. Looks interesting. So it says that if n squared divisible by 4, then n is divisible by 8. For example, let's go with the example. If n squared is 64, it's divisible by 4, then n, we know that it's 8, so it's also divisible by 8. So kind of looks like correct, right? But if I, for example, take another integer, let's say for a, n equals to 6. Here, n squared is 36. Yes, it's divisible by 4, but n 6, I'm going, if this one is start from this part. So if this part is divisible by 4, yes, correct, but 6 is not divisible by 4. So this statement is incorrect. So here I brought one counterexample to disprove this statement. For B, if n is integer, then n squared plus 1 is a prime number. Oh, looks good. So let's say if n equals to 1, 1 squared plus 1 equals 2 is a prime. Correct. If n equals to 2, 2 squared plus 1 equals to 5. 5 is also prime, but if I go, for example, with 3, n equals to 3, 3 squared plus 1 equals to 10. 10 is not prime number. If you remember, prime number is what kind of numbers? Numbers which can be divisible by 1 and itself, but 10 is not prime number. Or also, for example, n equals to 5. Does not hold for n equals to 5 also. So 5 squared plus 1, it will be 26. 26, again, not prime number. It's even number. So here by any, you can go with a 3 or 5, you can give counterexample and disprove it. Part C, if an integer is a multiple of 10 and 12, then it's multiple 120. So the first number which comes to my mind is 120. So they are multiple of 10 and 12, then it's also multiple 120. Or if n equals to, for example, if your number is 240, they are multiples of 10 and 12, and they're also multiple 120. But the first number which counts less than 100 is 60. If n equals to 60, yes, it's multiple of 10 and 12, which is correct, but it's not multiple of 120, right? As you can see, so n equals to 60 is a counterexample for this statement. So we are kind of disproving the statement. It's also types of proof. Now, the next part is proof by contradiction. Also, it's called reductio ad absurdum. I don't know, maybe it's in Harry Potter style type. Yes, what's a contradiction means, how it works. Here it comes. Here I brought from when, okay, if they say by proof by contradiction, what do you need to follow? Identify what is being implied by the statement. Implication is if something, then it happens. So this one is implication, right? So you find first in your statement what's implied. We first find what other implications are. So then from there, what's the step is assume the implication is false. So we kind of negate the implication. We say, for example, if my implication apples are red, my assumption apples are not red. So I'm kind of negate what's assumption is negation, then used by mathematical theories, axioms to arrive to the contradiction. So we should arrive to some absurd stuff. If we arrive to this stuff, then we say that our assumption was incorrect. So we find the implication, we then always assume that implication is false. implication is false. I will give examples. Implication is false. So then we kind of will go with this implication, and we should come to some nonsense, which does not make any sense in mathematics. Then we say that our assumption was incorrect, then our original statement is correct, is true. So that's the idea. Let's see with the examples. Okay, prove by contradiction. If the n is integer, so it's a condition. If integer is odd, then n squared is also odd. So what does contradiction say? First, we found the implication, n squared is also odd. So first what we do, we assume n squared is not odd, even. Okay, we are thinking that it's false. So it's even. So what n squared is even means? N squared even means that there's such number k. When I multiply by 2, it will be given. So we, again, how do we show even numbers? By 2k, odd numbers by 2k plus 1 or 2k minus 1. So there is no big difference here. So it means that n squared equals to 2k. So what does it mean? N times n equals to 2k. But here it doesn't make any sense. We say that n is odd. We know that multiplication of two odd numbers never even. It's always odd. If you imagine take any two odd numbers, when you multiply them, it's always odd, not even. So this one does not make any sense. So I thought the assumption is even, but then we thought the n is odd. It doesn't make any sense. So we said it. We find by contradiction. We find by contradiction that n squared can't be even. So if our assumption is incorrect, then it means that the first statement was correct, was true. N squared must be odd. Let's see some more examples. Prove that there is no real number x such that, okay, it holds this equation. Okay, let's assume that there is such number. Which number? Okay, I don't know. Let it be b. Okay, assume there is such number which satisfies this equation. Okay, if there is, let's see what it is. We can find it, right? So it will be 1 equals, if I cross multiply it, 1 minus b minus 2. If we open the brackets, it will be b minus b squared minus 2 plus 2b. If I call it all there in one side, it will be b squared minus 3b, and it will be plus 3 equals to 0. Okay, let me try to find this b. Now I am going to use quadratic formula. So if I go with the quadratic formula, what will be? b equals to 3 plus minus the discriminant 9 minus 4 times 3 divided by 2. Now here, as you can see, inside the square root is negative. It's actually not real number. It's a complex number. So here we found by contradiction that there is no such. Our assumption is incorrect. So the first statement was correct. Okay, and there is one more, the classic question. Also in your book, you have some problems, 10 and 11. Check them. I will try to solve here kind of similar but different with numbers. Prove that. It's very common question. It's very classical question. Prove that square root of 5 is irrational. What's irrational means? It means that you cannot write root of 5 as a fraction of two integers. So this irrational means that you cannot write it. So what we will do here, we will prove it this type of way by contradiction. We will first assume, we will make an assumption. Assume that we can write it, a divided by b. Okay, we could write it. And here I will assume that a and b are already simplified. So I don't want to have this case, for example, 2 divided by 4, they give you the same thing, 4 divided by 8, they give you. I want the simplified form. So I will assume that a and b are already in simplified form. and b is different than 0, right? If b is 0, it doesn't make any sense. So a and b are integers and b is different than 0. Okay, if I square these two numbers, what will be 5 equals to a squared b squared, and if I cross multiply, 5b squared equals to a squared. Now look from here. What does it mean? A is actually multiple of 5, right? A is multiple of 5. So I can write that A is 5 times some number k, k is an integer. A must be multiple of 5. So from here, if I rewrite again in this statement, what it will be, 5b squared equals to 25k squared. I just instead of a put 5k. And from here it also seems that b is also multiple of 5. So I can write b as 5 times m for some m of integer. Okay, now from here it I found something nonsense because I made the assumption that a and b always simplified form, but here I keep finding the numbers with the multiples of 5, so I cannot find in simplified form. So here I contradict my assumption. Okay, I contradict my assumption, so it means that the first original statement is true, is correct.